1.4 quadratic equations continued. In the last video, we talked about completing the square. And we did examples using numerical values. First thing I want to do in this video is I want to complete the square, but I want to use everything as a variable. So starting with ax squared plus bx plus c is equal to 0, I want to complete the square. So remember, the first thing we want to do is we want to get the leading coefficient to be equal to 1. So we're going to divide by that leading coefficient, which happens to be a. So dividing by a, we get x squared plus b over a x plus c over a is equal to 0. 0 divided by a is 0. The next thing we want to do is move the constant term. Notice there's no variable in this term. We're counting x as the variable. Yes, I know a, b, and c are variables, but not what we're talking about, right? So we want to move this constant term over to the other side by subtracting it. So x squared plus b over a x is equal to negative c over a. Okay? Next step, we want to divide this by 2 and then square it. If we divide b over a by 2, that's b over 2a, right? 1/2 of b over a. So b over 2a. If we square that, we have b squared over 4a squared. So plus b squared over 4a squared. If we add it to this side, then we have to add it to the other side. Plus b squared over 4a squared. Okay, so we're to that point. Realize that b over 2a was the value that we squared, so that means this can be rewritten as x plus b over 2a squared is equal to negative c over a plus b squared over 4a squared. Before I use the square root property, I'm going to get a common denominator here and kind of pull this together. So I'm going to leave this as x plus b over 2a squared for a moment and say, well, I've got a here and 4a squared there, so if I multiply this side by 4a, that's going to give me 4a squared. So I'm going to have negative 4ac over 4a squared plus b squared over 4a squared. That's a 4, not a b. 4a squared, which now that I have the common denominator, I can rewrite that as negative 4ac plus b squared over 4a squared. Okay, so I just added them together now. Now if I use the square root property, I have x plus b over 2a is equal to plus or minus the square root of negative 4ac plus b squared over 4a squared. I subtract b over 2a from both sides. X is equal to negative b over 2a plus or minus the square root of negative 4ac plus b squared over 4a squared. Now I notice here, first of all, I see I've got a minus and I've got a plus. So if I change the order of those two, I'll have a plus then followed by a minus, so I can have a positive value minus something. And I see that 4a squared is a perfect square. 2a times 2a is 4a squared, so I can get rid of that. So I have x is equal to negative b over 2a plus or minus the square root of b squared minus 4ac over 2a, right? I just moved the b squared before it, so b squared minus 4ac. And the square root of 4a squared is 2a. So to finish this off, and I'm going to put this in red, right in this area right here, I find that x is equal, notice we have a common denominator, 2a, is equal to negative b plus or minus the square root of b squared minus 4ac over 2a by going through and solving this manually using completing the square. Now that may look familiar to you. That is what is known as the quadratic formula. The quadratic formula, x is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. Now many of you may have been taught this is the quadratic formula, and you were never shown why or where it came from. They just said memorize this. I know that's how I was taught many, many years ago when I was taught the quadratic formula. They said if you want to solve a quadratic equation, you can use the quadratic formula, which is negative b plus or minus the square root of b squared minus 4ac over 2a. I've even had some students sing me a song that they were taught to help them remember this. The reality of it is the quadratic formula works and is valid because it is simply completing the square. If you start out with a quadratic equation in standard form, ax squared plus bx plus c is equal to 0, and go through and complete the square, you end up with the quadratic equation. Sorry, the quadratic formula, which is the thing that you were taught way back when. Now, I hope some of you started to catch things when you saw the minus 4ac and the b squared and this 2a and stuff like that, that you went, wait a second, this looks a lot like the quadratic formula. And yes, it is. So now that we've done this, we can use the quadratic formula to solve quadratic equations. And as many of you may attest, the quadratic may make solving quadratic equations much simpler than any of these other methods, especially if you have a complicated quadratic equation that you're dealing with. Also, no matter how much I love completing the square and how good I am at it, you gotta admit, if you can remember the quadratic formula, it's going to be much faster and easier than going through all those steps to get there using completing the square. But the key thing is if you remember the formula. So make sure you know that formula. I'm going to write it right up here again. X is equal to negative b plus or minus the square root of b, sorry, my b looks like a 6. B squared minus 4ac over 2a. And I'll be perfectly honest with you, I am horrible at memorizing formulas, always have been. And things like this where they told me just come up with this, remember that equation, was just a nightmare. I could never remember the quadratic equation. The only reason I can remember it now is one, I know how to complete the square so I can go through and I can find it whenever I need it. And two, I've been doing this for so many years that finally it's been beaten into my head that this is the quadratic formula. Okay, so let's put it to use. Let's say we have x squared plus 6x is equal to 3. Now, in using the quadratic formula, just like any other time we've dealt with this, solving a quadratic equation, we want it equal to 0. So x squared plus 6x minus 3 is equal to 0. Now, at this point, we may look at it and say, well, first thing we look at is, can we do a basic factoring? Can we use the zero product rule? Two numbers that multiply to negative 3 and add to 6. Okay, right there that tells us no, because there's no way I'm going to multiply two numbers to negative 3 and come out with a positive 6. This says they have to have opposite signs, and the one number has to be at least 6, has to be 6 larger than the other number. There's no way it's going to happen. So we eliminated that. Could we do this by completing the square? Sure. But what do we have here? We have x is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. So we can just start plugging in. X is equal to negative b. b is 6, so negative 6 plus or minus the square root of 6 squared, right? b squared minus 4 times a is 1 times c is negative 3. Be careful, don't lose those negative signs. Over 2 times a is 1. Okay, so now that we have that, negative 6 plus or minus the square root of 6 squared is 36. 4 times 1 times negative 3 is negative 12, so minus negative 12 is plus 12. 2 times 1 is 2. X is equal to negative 6 plus or minus the square root of 36 plus 12 is 48. Over 2. Now I happen to recognize that 48 is 3 times 16. 16 is a perfect square, so I can pull out the square root of 16, which is 4. So x is equal to negative 6 plus or minus 4 radical 3 over 2. Excuse me. And then I see I've got negative 6 and 4, and I've got a 2. I can factor that 2 out of everything, which gives me x is equal to negative 3 plus or minus 2 radical 3. And I have solved it using the quadratic formula. Yes, I took a number of steps to do it because I showed everything along the way, but in reality, we had to get it so it was zeros on the one side, we plugged everything in, we performed the math, which there's nothing that would have stopped you from saying 36 minus a negative 12, so 48, all in one step instead of writing that all down there. And then I factored out, and I recognized I had a perfect square in there, so I factored it out and then simplified. And trust me, you would have had to do the same simplifications and everything if you'd used completing the square, and it just would have taken you longer to do it. So not bad, that worked pretty well. Let's grab another example. Four x squared is equal to 3x minus 5. Now you may ask me, well, Mr. Davis, why for the quadratic formula do you keep giving me these ones where it's split up all over the place? Well, basically, you had enough to worry about dealing with completing the square that I didn't want to throw in all these extra bits and pieces with it. The same thing could happen with completing the square, where you figure, why not give you that extra step since all you're going to do is plug the values into here anyway. Just be careful because a common mistake is people go, oh, x squared x, and they say a is equal to 4, b is equal to 3, and c is equal to negative 5. In reality, that's not the case because once we move these over to the other side, you have 4x squared minus 3x plus 5. So a is equal to 4, b is equal to negative 3, and c is equal to positive 5. So common mistake, they look at this and they just start grabbing a, b, c, and that's not correct. It's actually a, negative b, negative c. So always make sure you write it in this form. Then you can use the quadratic formula. So negative, negative 3. And yes, I do that. Notice it's negative b. I will always put that negative in front and then plug my b value in. The main reason I do that is so that I don't look back later and go, wait a second, because if I just go negative, negative 3, well that's 3, and put that in my first thing, I may look back later and go, wait, oh, it was supposed to be negative b, and I put another negative sign in and it throws everything off. So with this, I know I took negative of whatever b was, so I actually write that out. Plus or minus the square root of b squared, so that's negative 3 squared, minus 4 times a, which is 4, times c, which is 5. Extend my radical, make sure it makes it out all the way, right? Over 2 times 4. I like to make sure I've got it all plugged in there and I can look at this and say, okay, minus b. b was negative 3, so negative 3, got it. b squared, negative 3 squared, okay. Minus 4 times a was 4, c was 5, 2 times a was 4, and I can look back easily and verify that I plugged in all the values. If you start doing things as you're plugging it in, it's much harder to check your work later and much easier for you to mix something up. So now that we've got that, x is equal to negative 3 is positive 3. Now I start going through and doing this. Plus or minus the square root of 9 minus 16 times 5 is 80. 80 over 8. X is equal to 3 plus or minus the square root of 9 minus 80 is 71. Over 8. At this point, you're kind of sunk. That's as far as you can go. Unless we estimate what that value is. So I would leave it just like this. We don't need to split it up to 3/8 plus or minus the square root of 71 over 8 because this isn't a complex number. So we're not putting in the form a plus bi. We're just simplifying as far as we can. If this came out to be something that we could easily work with, then we could have simplified further and possibly even split it up into the two pieces. But in this case, it did not. So let's try one more. Actually, let's do one more problem of a similar type, but we're going to take it a step further. Now, solving a cubic. Well, we're dealing with quadratics, and now I'm saying solving a cubic. A cubic is a polynomial that has a third degree polynomial. So let's say we have x cubed, it's supposed to be a cubed, minus 125 is equal to 0. Now, we may look at that and already be like, whoa, what's going on here? But I'm going to point out that 125 is a perfect cube, x cubed is a perfect cube, and there is a special product associated with this. X cubed minus y cubed is equal to x minus y. Let me get minus y, make sure I get it right. Yep. Plus, I'm sorry, not plus. Multiplied by x squared plus xy plus y squared. Oh, there we go. Make sure we write everything down correctly. So x cubed minus y cubed is equal to x minus y times x squared plus xy plus y squared. There's also another one that's x squared plus y squared is equal to x plus y times x squared minus xy plus y squared. Okay, so this, a perfect cube minus a perfect cube, can be factored out to this using this special product. We have a perfect cube. This is actually x cubed minus 5 cubed is equal to 0, which means I can use this and say, well, then that's x minus 5 times x squared plus 5x plus 25, or 5 squared, is equal to 0. Well, now that we have that, we have a binomial and we have a quadratic. Well, how can we solve this quadratic part? We can use the quadratic formula. So we've got to remember that this one exists. Don't lose that factor. So we can look at this and go, okay, well, x is equal to, in fact, let's just do this right now. X minus 5 equals 0, x is equal to 5. Right? So we've got that as one solution. Just so we don't lose it and forget about it. So we can say x is equal to negative b, so negative 5 plus or minus the square root of 5 squared minus 4 times 1 times 25 over 2 times 1 is equal to negative 5 plus or minus the square root of 25 minus 100 over 2 is equal to negative 5 plus or minus the square root of negative 75 over 2. This being a negative in here, we can pull out I. Also, 75 is 25 times 3, so 25 is a perfect square, so we can pull out 5. So we get is equal to negative 5 plus or minus 5i square root of 3 over 2. And with this one, you see that we do have imaginary part, so it would probably be a good idea to say x is equal to negative 5 halves plus or minus 5i square root of 3 over 2. So that's a possibility of what we could do to finalize that. Let me make that look more like a 2u. Okay? So, and in this case, dealing with this where we're ending up with a radical in here and the imaginary, would actually be perfectly fine with you saying x is equal to that and x is equal to this. So we've got 3 roots, x equal to 5, x equal to negative 5 plus 5i square root of 3 over 2, and x equal to negative 5 minus 5i square root of 3 over 2. If you take it to this, I'm perfectly happy also. So I would accept either one of those as a correct answer. But notice what happened here. We now have one real root, and we have 2 complex roots. So let's look at the quadratic formula and how we can determine, sorry, picking up that eraser that dropped. How can we determine whether we have complex roots, real roots, and how many of them there will be? So I'm going to leave this up here, and I'm going to look at this, and I'm going to say, this here, we've got the square root of b squared minus 4ac. b squared minus 4ac is known as the discriminant. And I take no blame if I spelled discriminant wrong. I will look to see if I have it written down here so I can cheat. Discriminant. There we go. I'm a math teacher, not an English teacher. I don't have to spell things correctly. Okay? So that's known as the discriminant. And the discriminant makes the decision, or makes it obvious to us, how many and what type of roots we're going to have. Because if we look at this, we realize that if b squared minus 4ac is equal to 0, if that is equal to 0, then we're just going to end up with negative b plus or minus 0. Well, if you add or subtract 0, it doesn't change anything. You just end up with negative b over 2a. Which means you're going to have one real rational root. If the discriminant b squared minus 4ac is equal to 0, you will have one real rational root. Real because you're going to have some value divided by 2 times some other value, so you're going to have an integer divided by an integer, or even if it's not an integer, if it's a decimal to some point, you're still going to have it, or even if it's a fraction to some point, you're going to have a rational number. So it's one real rational root. If b squared minus 4ac, oops, put a 2 instead of a c, is greater than 0, so it's positive, then you're going to have two real roots but I'm going to break this up into two parts. If this is not only positive, but it is a perfect square. Or actually, let me just do a dash or an asterisk, right? If it's a perfect square, if this is a perfect square, then this radical, take the square root of a perfect square, you're going to get an actual value, a real number, then it's going to be, you're going to have two real rational roots. So I'm going to say rational here. So if b minus 4ac is greater than 0, you're going to get two real roots. If it's a perfect square under this situation, those two real roots are going to be rational. If it's not a perfect square, then they're going to be irrational. So either way, if the discriminant is greater than 0, you're going to have two real roots. If the discriminant's a perfect square, in that case, you're going to have we're going to have two rational real roots. If it's not a perfect square, you're going to have two irrational real roots. And then, if b squared minus 4ac is less than 0, then you're going to have two complex roots. Two complex roots because if this is less than 0, you're going to take the radical of a negative number, which is going to put an I in here. So, and you're going to have b plus or minus some imaginary value. So that's going to put you down to two complex roots. So if the discriminant's equal to 0, you have one real rational root. If it's greater than 0 and it's a perfect square, you have two real rational roots. If it's greater than 0 and it's not a perfect square, you have two real irrational roots. And if it's less than 0, you're going to have two complex roots. So there we go. So that's using how we can use the discriminant to determine how many and of what type roots we're going to have. So let's look at a quadratic equation and determine how many and of what type the roots will be without performing the quadratic formula. Actually, this can be used to help us so that when we do the quadratic formula or we complete the square, we can look at the results and say, did it come out with what we know it should be? So let's say I have 3x squared minus 7x plus 2 is equal to 0. Okay, so if that's the case, then if we want to know how many, what type of roots, we're going to say b squared, so negative 7 squared, minus 4 times a times c. So that's 49, I'll just bring it down here, 49 minus 6 times 4 is 24, 49 minus 24 is 25, 25 is positive, and it's a perfect square, therefore we are going to have two real rational roots, two real rational roots, because this is greater than 0 and a perfect square. So not bad. Let's try another one. Four x squared minus 3x minus 5 is equal to 0. So we plug it in, and we get negative 3 squared minus 4 times negative 5 is equal to 0. So we get 9 plus 80 is equal to 89. It is greater than 0. It is not a perfect square. Two real irrational roots. Just by looking at the discriminant. When we find that out, we can guarantee that we have two real rational roots. Then we can go through and we can do the work and we can show that we have the two real rational roots. Okay? And that finally, sorry, I went out of screen, that finally finishes up section 1.4 on quadratic equations.